everyone, my name is Lakshmikant, and in this video we will explore the response of a piezoelectric sensor. In this experiment we are going to plot the magnitude and phase response of the sensor, identify its resonant frequencies and calculate the quality factor of each resonance, and let's break it down step by step. The major purpose of this experiment is to analyze how the piezoelectric sensor behaves when subjected to different frequencies. By doing this, we can observe its frequency response, which will help us identify its resonant frequencies, the frequency at which the sensor efficiently resonates and responds. Additionally, we will also calculate the quality factor of each resonance, and we'll tell about how the sharpness and damping of the resonance works.
Hello, myself Lakshmikant. For this experiment, we set up a basic circuit where the piezoelectric sensor is connected to a signal generator and an oscilloscope. The signal generator sweeps through a range of frequencies, sending signal to the piezoelectric sensors. The oscilloscope measures the output signal, and we record both magnitude and phase of the response at each frequencies. The piezoelectric sensors convert mechanical vibrations into an electrical signal, and its impedance or reactance vary with the frequency of the input signals. By measuring the voltage across the sensors, we can determine its frequency response. Come on, let's see the circuit. We have taken our input from the signal generator and giving it to the connecting it to the piezoelectric sensor. From there, we are taking the output and connecting it back to the our oscilloscope through channel 1. So channel 1 gives us the output. We have also plotted our inputs through channel 2, connecting it to our signal generator, so we can see the electric signals that are generated as an input in a wave format.
Hello, now I'll be explaining the magnitude response. The magnitude response is essentially the strength of the sensor's output signal relative to the input signal at each frequency. As we sweep through the frequencies, we expect to see peaks in the magnitude response at resonant frequencies. Here, we can see a peak at 200 Hz and 2000 Hz respectively of the frequency from 0 to 14,000 Hz and magnitude gain from 0 to 3. How do we express the magnitude? It is expressed in terms of decibels, using the formula 20 log to the base 10 of h of f, where h of f is the frequency response of the sensor. These peaks corresponds to frequency where the sensor resonates and absorbs energy most efficiently. Next, I'll explain the phase response. The phase response tells us how the phase shift between the input and the output signals at each frequency. A change in phase can occur when the sensor reaches resonance, which reflects how the sensor's impedance changes with frequency. The phase response helps us understand how the sensors behave, shifts at different frequencies, and it's particularly useful for identifying the point of the resonance. How do you identify resonance? In order to identify resonance, we must know its resonant frequency by knowing the sharp peaks in the magnitude response plot. These frequencies are where the sensor resonates most efficiently by absorbing the most energy. By looking at this point, we can know where the resonant frequencies occurs. We can see over here the quality factor and the resonant frequency. The quality factor is 0.1 for the resonant frequency 200 Hz, and the quality factor is 1 for the resonant frequency 2000 Hz. Now, in order to calculate the quality factor, we must know what a quality factor is. The quality factor, or a Q factor, is a dimensionless number that quantifies the damping of the system. It tells us how narrow or broad the resonance is. A high Q indicates a sharper resonance. Over here, a higher Q is 1 for the resonant frequency 2000, and the lower Q is 0.1 for the resonant frequency 200 Hz, which implies it has more damping and a broader resonance. To calculate Q factor, it is f of r by delta f, where f of r is the resonant frequency and delta f is the bandwidth of the resonance, which is the difference between the frequency at which the magnitude drops by 3 decibels from the peak. For the conclusion. In the conclusion, this experiment helps us how to identify a piezoelectric sensor which reacts to different frequencies, and it characterizes its behavior through magnitude and phase responses. We also learned how to calculate the quality factor, and what does the resonant frequency actually mean. Thank you for watching the video.
Hello. In this photodiode experiment, we will explore the frequency response of a photodiode. We will be measuring both the magnitude and phase response across a range of frequencies. The key objective is to determine the 3 dB cutoff frequency, which provides insights into the bandwidth and the operational speed of the photodiode.
Hello, I'll be explaining the circuit. The photodiode is connected in a reverse bias configuration with a resistor in series. The voltage across the resistor is measured as the output. When the photodiode is illuminated, it generates a photocurrent which is converted into
We are
a
taking the
voltage
signal
Let's
through
analyze
the
circuit
channel
now.
1 of the signal generator and connecting it to our LED, which is in the breadboard. Now we have connected the resistance of 330 ohms in series with the LED. The photodiode is kept parallel to the LED. The photodiode is kept very close to the LED because it must maximize its efficiency. The photodiode is in reverse bias and 5 volt is provided from the breadboard and is connected to the negative terminal of the photodiode. This is also connected by a resistor of 10,000 ohms in series with the photodiode. Another point of the resistor is it's connected to the ground. We are also connected the channel 2 of the oscilloscope for the input of the photodiode.
Now, let's examine the frequency response of the photodiode. We apply a modulated light signal across a range of frequencies and measure the output voltage. The magnitude response reveals how the output amplitude changes with frequency, while the phase response shows how the signal phase shift as the frequency increases. At lower frequencies, the magnitude response remains nearly constant. As the frequency increases, the magnitude response begins to drop, reflecting the bandwidth limitation of the photodiode. The phase response shows a shift which corresponds to the time delay in the signal due to the photodiode frequency characteristics. Here is the phase response graph. Next, we focus on the 3 dB cutoff frequency. This is the frequency where the magnitude response drops to 70.7% of the maximum value, indicating a 3 dB reduction in the signal power. The 3 dB cutoff frequency defines the bandwidth of the photodiode and provides an understanding of its speed of response. The 3 dB cutoff frequency is crucial for understanding the photodiode performance in high-speed application. Like you can see that we can find out 3 dB cutoff frequency by this formula and take the frequencies. So by using this formula we can find the 3 dB cutoff frequency. A higher cutoff frequency typically indicates faster response, which is essential for applications such as optical communication and high frequency signal detection. Yes, you can see in the graph we have plotted the 3 dB cutoff frequency. So our frequency 3 dB cutoff frequency comes out nearly to be 78,000. In summary, we analyzed the frequency response of the photodiode, plotted both the magnitude and phase response, and determined the 3 dB cutoff frequency. The process is essential for selecting photodiode for applications that require high-speed signal processing.